Welcome to AP Physics Podcast. This is question number 35. In it we have a bullet embedding itself into a block. And we are asked, based on the information that we are given, to find the angular velocity of the system after the collision. In order to find the angular velocity, one of the easiest ways would then to be finding the angular momentum, because angular momentum is equal to I times omega. Now, if we consider the bullet and the mass, or the block, to be part of the same system, we find that our total external torque is equal to 0, which means that we can say our momentum is conserved, angular momentum is conserved, and L initial equals L final. So our L final is I final times omega final. And before the collision, what is moving? Well, the bullet is moving. And so we find that our L initial then, in using the R crossed with P idea, is equal to L times the mass of the bullet times the velocity of the bullet. So our L initial then is mvl, since the bullet is moving in a perpendicular path to our radius. So mvl, that's our initial angular momentum, and that's equal to our I final times angular velocity final. Our I final, we can consider these to be point masses, since our rod is of negligible mass. So it will be the sum of mr squareds. In this case, our mass is both in the same location, and it is mass little m plus big M, and our r is L squared. So we end up seeing then that mvl is equal to m plus m L squared times omega final. So we find that our final angular angular velocity of the system after the collision is equal to one of the L's will cancel out, so we're left with mv over m plus m times L. For part B in this problem, we're looking for the fraction of kinetic energy lost in the collision, which means we need to look at the kinetic energy before the collision minus the kinetic energy after the collision, and we'll divide that by the kinetic energy before the collision. Now, our kinetic energy before the collision, the only thing that is moving is the bullet, so we have 1/2 m times v squared. After the collision, we have 1/2 both masses, m plus m times v final squared, and we're going to divide that by 1/2 m times v squared again. So the question is then, what is our v final? Well, we know our omega final times our r, which in this case is length, is going to equal our v final. So we end up getting that v final then is equal to mv over m plus m. If we take that information, we plug it in right up here and simplify that down, we will end up finding that our ratio that is lost is big M over little m plus big M.